want to take you through some applications of the principle of inclusion exclusion. And of course, those are super important because we're going to continue to build on this. So it's important that we understand the basics before I get you into anything further where things are not in the right place, or I'm looking for at least or at most, etc. So let's take a look at a sample question. This is a linear equation application. How many integer solutions are there to x1 plus x2 plus x3 equals 12, where x sub I is between 1 and 4 for all I 1 to 3, which is essentially saying this guy is between 1 and 4, this guy is between 1 and 4, inclusive, and this guy is between 1 and 4. That's all that's saying so far. Now, here's what I know. I know that all of the values are at least 1 because it tells me right here. x1 is at least 1 and at most 4. So what I'm going to do is I'm going to subtract 1 from each of those, which means that after subtracting 1, I'm going to call this x1 prime, which means it's not the x1 I started with. I've taken 1 away. x2 prime and x3 prime are now equal to 9 because 12 minus 3 is 9. And notice I've shifted this from 1 to 3. Nope, I've shifted this from 1 to 4 down to 0 to 3. I really like to have that 0 here. It makes it a lot easier. Okay? Now we're going to say we're going to let C1 be that xi is greater than or equal to 4. So why am I doing that? Well, because I know that 4 is not okay. Remember, I'm saying I want to find this only works from 0 to 3. So from 4 on to infinity, those aren't okay. So if I set this condition to be greater than or equal to 4, then I'm really going to be looking for not Ci. Not Ci I know how to find because we've just been working on finding not Ci. So to solve this question, I'm really looking for not C1, not C2, not C3, because that's what I've set my conditions to be, is that they're values outside of my range. So hopefully that makes sense. This is just a repeat of everything we know that says if you want to find not C1, not C2, not C3, you take the universe, you subtract elements, or the number of elements in set size 1, add set size 2, subtract set size 3, etc., which may also end up looking like this. So really all I have to do is find each of those 4 values. So our job then is to find the values of S0, S1, S2, S3, etc. Now, S0 is just the number of elements in the universe. So really, I'm starting with this question, but remember that on the last page I rewrote this to say x1 prime plus x2 prime plus x3 prime are equal to 9 because I used the fact that they were all at least 1. Then I said, and of course I said that now 0 is less than or equal to x sub I is less than or equal to 3. Then I made my conditions. C1 is that x1 is greater than or equal to 4, because now it tells me I'm going to be looking for not C1. C2 is that x2 is greater than or equal to 4. C3 is that x3 is greater than or equal to 4. So let's take a look now at kind of putting together the principle of inclusion-exclusion, as well as something that we've already talked about, which is combinations with repetition. What I'm saying is, now I have 3 boxes. And those 3 boxes, the number of elements I put into each box have to add up to 9. So I have 9 items to place. So I could place 3 and 3 and 3. So that's one of the different ways I could do it. I could place 2 and 2 and 5. That also adds to 9. So you get the idea that there are a lot of different combinations, and I'm much too busy to come up with all of them. I just want what's the total number. So let's use combinations with repetition that says I have 3 boxes, I have 9 items to place. Remember, combinations with repetition says 3 choose 9 is 3 plus 9 minus 1. So I would subtract that 1, choose 9, and that's where 11 choose 9 came from. Now, could I get my calculator out and determine what 11 choose 9 is? Yes. You don't need to do that. So notice in my final answer, I'm including 11 choose 9. I would not include combinations with repetition 3 choose 9 because I would want to write it as a normal binomial coefficient. Now we're going to apply that one condition is met. One condition only. So if one condition is met, essentially I'm saying C1 is met. Let me use a different color. So I'm saying, let's say C1 is met. Well, if C1 is met, then C1 is at least 4. So I could take 4 away from here and here, and that gives me that x1 double prime plus x2 prime plus x3 prime is equal to 5, which means now I have 3 boxes and 5 items to place. 3 boxes, 5 items to place is 3 plus 5, which is 8, minus 1 is 7, choose 5. But it would happen for x1, then for x2, then for x3. So how many times will it happen? It will happen the 7 choose 5 times 3 choose 1, because it's 3 times 1 for each one. So I'm saying there are 3 conditions, one of the conditions is met. Then let's look at if 2 conditions are met. So if 2 conditions are met, I would say that not only am I subtracting 4 for x1, but I'm saying x1 double prime plus x2 double prime, which means I'm subtracting 4, plus x3 prime is equal to 1. That's where this came from. So I have 3 boxes, but I just have 1 item to place, so it's combinations with repetition, 3 choose 1. So 3 plus 1 is 4, minus 1 makes it 3, choose 1. Again, this is happening 3 times, but I'm choosing 2 conditions. So 3 conditions, choosing 2 of the conditions. Then if I tried to do that for all 3, where all 3 are greater than 4, we can see that if I subtracted 4 again, I would end up with a negative number. So it's very clear that S3 is actually 0, or the number of elements in the union of all 3 sets is 0. So what's my final solution? Again, notice that I did not find any of the actual values. I'm writing it just like this. I'm saying here's the number of elements in the universe. Here's the number of elements where 1 condition is met. Here's the number of elements where 2 conditions are met. And of course, subtracting 0 for when 3 conditions are met. That's my final solution. Let's take a look at another application of the principle. How many onto functions are there from a set with 6 elements to a set with 3 elements? So remember that what I'm dealing with is I've got 6 elements here, and I've got 3 elements here, and it says let's let the codomain be ABC. So C1 is that A is not in the range, C2 is that B is not in the range, and set C3 is that C is not in the range. So far, hopefully you're with me. So why did I say not in the range? Because my question is actually that they are in the range, so I want the not in the range. You get the idea? We always do the opposite so that I can then find not C1, C2, C3, which means I get to use my handy-dandy little formula that we've been working with. So remember that onto functions are functions that each element in the range maps back to only one element in the domain. So first I'm looking for not an onto function, I'm just saying how many functions exist from a set with 6 elements to one with 3 elements. So again, I'm looking from this direction. This guy can go back to 6 different values, this guy can go back to 6 different values, and this guy can go back to 6 different values. So 3 values, each to the 6th. Then I'm saying, let's say C1 is true. C1 being that A is not in the range of the function. So if I took A out, I just have B and C. So now I have two elements, each with 6 options, but I have 3 conditions and I'm choosing one of them, which means it's happening for C1, and then it's happening again for C2, and then it's happening again for C3. So basically it's saying we're taking 3 times 2 to the 6th is really what's happening. Then we're saying let's let 2 conditions be true, which means A and B are not in the range. Well, then I only have one guy to the 6th power, but that's 2 conditions. There's 3 of them, 3 choose 2 conditions, which is the number of functions that don't have 2 elements in the range. And then, of course, the number of elements that don't have 3 in the range would be 0, because that has to map to something. So, using this formula, I'm really just adding and subtracting the values that I need to. 3 to the 6th minus 3 times 2 to the 6th plus 3 times 1, which is 3, which gives me 540 total. So notice on this one I did go ahead and figure out the answer. Really either one would do. So if I kept it as 3 to the 6th minus 3 choose 1, 2 to the 6th plus 3 choose 2, 1 to the 6th, that would be just fine as well. Now you're going to get a lot of questions dealing with onto functions, so just to generalize so that you have something to look back on, we already know that the answer is 540. We've worked it out together, but let's take a look at a generalization of the function. It says, hey, if you want to find s sub I, so s sub 0, s sub 1, etc., we're essentially going to find n choose k, where n is the number of elements in the codomain. Remember, codomain is just range. M represent the number of elements in the domain, but that's our x's. Here's our y's. And k represent the number of conditions met. Perfect. Then we can generalize essentially that each one looks like this, or again you can use that summation notation with a -1 that helps you to remember that we're alternating between pluses and minuses. But essentially if I'm using this, I'm saying 3 choose 0 because there are 3 conditions and 0 of them are met, because that is s sub 0 that I'm looking for. So in this case n is 3, k is 0. This would be 3 minus 0, and then m is the number of elements in the domain, which remember was 6, so that's why I'm taking it to the 6th. That's what gives me 3 to the 6th. And then I move on to one condition is met, so I'm changing k from 0 to 1, but everything else is the same, so now I'm saying 3 choose 1, and then 3 minus 1 to the 6th, and then I'm saying 2 conditions, so 3 choose 2, 3 minus 2 to the 6th, and then 3 choose 3, 3 minus 3 to the 6th. And notice, using that, I get the exact same answer as before. So I have 2 questions to finish this out, and they're both questions that I'd really like for you to try. It really is helpful, even if you struggle with this, to get as far as you can on your own before you press play to see how I approach the problem. Also keep in mind there's more than one correct way to approach the problem, so I am going to go through this the way that makes most sense to me. But if you have a way to go through it, again, we're still using the principle of inclusion-exclusion, so just make sure you're using that to solve this question. So this question says, how many arrangements of combinatorics have no consecutive pairs? So before I do anything else, I would count the number of letters, and I've counted the number of letters total, and there are 13 letters. I also would want to remember that I've got some repeats of letters. So if you'll notice, I've got 2 C's, I've got 2 O's, and I've got 2 I's. And all of the rest of my letters are singles, which is great. So why is it important to know what repeats I have? Because if I started to rearrange these, and I had the 2 C's together, and then Combinatorics, this would be the same as if I switched these 2 around, because it's the exact same nonsensical word, still 2 C's together. So why do I bring that up? Because if you'll recall, the first thing I want to do is find S sub 0, which is the number of elements in the universe. Well, if there are 13 letters, the easy way is 13 factorial, but it's not that easy because I've got the two C's that could end up together, I've got the two O's that could end up together, and the two I's that could end up together. So that's the number in the universe. What would we do for our conditions? Well, our conditions, because we want no consecutive pairs, that means when we write our conditions, we're saying we do have consecutive pairs, because we always do the opposite, so that when I'm finding my solution, I'm finding the no consecutive pairs. So C1 is that the two C's are together. C2 are that the two O's are together. C3 is that the two I's are together. So if I want to find S1, remember S1 would be that one condition is met. So either the two C's are together, the two O's are together, or the two I's are together. So how would I determine that? Well, it's going to kind of look like this, but what I'm going to think about is if the two C's are together, I'm just going to call that one letter. So the two C's are one letter, which means now instead of 13 letters, I have 12 letters. And how many pairs do I have? Well, I've already taken out a pair because I've said that those two C's are now just one letter. So now I've got the O's and the I's. So it's 12 divided by 2 factorial divided by 2 factorial. Why is it 3 choose 1? Because there are three conditions, and I'm choosing either that CC is together, or that OO is together, or that II are together. So that's S1. Then I'm going to do S2. And S2 says, let's fuse the two C's and fuse the two O's. So now I have 11 letters. I've got the two C's, I've got the two O's, and then I have everything else, which means I have 11 letters and just one pair, which is the I's in this case. Now, if I did the same for the two C's and the two I's, then that would be 11 factorial, 2 factorial. And then the two O's and the two I's, that would be 11 factorial, 2 factorial. And again, that's why we choose that 3 choose 2, because we're choosing two conditions. So it basically, so I don't have to keep writing 11 choose 2 that many times. Then we're going to say that all of them are together, which means I've got one fewer letter, because I've got CC together, OO together, and II together. So now instead of 13 letters, I have 10 letters. I don't have any repeats, so notice I don't have to divide by anything. And there are three conditions, and I'm choosing all three of them. So what's my final solution? I would just write it as 13 factorial, 2 factorial, 2 factorial, 2 factorial, minus 3 choose 1, 12 factorial, 2 factorial, 2 factorial, plus 3 choose 2, 11 factorial, 2 factorial, minus 3 choose 3, 10 factorial. That is my final solution. Here's your last practice question, and this one is a linear combinations question. So just to give you a start before I set you off on your own, we did a question like this before where we said, how many integer solutions are there for x1 plus x2 plus x3 equals 12? Essentially what I'm doing here is saying x1 plus x2 plus all the way up to x12, because there are 12 questions, has to equal 200 points. So you have 200 points on your final, there are 12 questions. So how many ways can I assign the point values to the 12 questions if each question must be at least 10 points, but no more than 25? And all point values are a multiple of 5. I'm going to let you figure that one out on your own. So think about how we could use the 10 and the 25 like we did before. And then what would your conditions be? How are you going to solve this question? So really do press pause and take your time going through this. When you're all done, press play to see how you did. And if you did it correctly, then kudos to you because this is a tough question. So again, first thing is exactly what I've already done with you. x1 through x12, the sum of those is 200. I've restricted them to be from 10 to 25 for all of the i's from 1 to 12, which means just for every single question, I being my subscript here. So I am going to first apply that each one must be at least 10. So I'm subtracting 10, subtracting 10, subtracting 10, etc. from each one. So essentially I'm subtracting 120 because there are 12 total. So again, that's going to give me now that my x prime values are between 0 and 15. So xi prime are between 0 and 15. And that's really the first step, is you want to take that into account. Then I'm going to apply, in this case, that all point values are a multiple of 5. So if I'm dividing by 5, then I'm getting x1 double prime, x2 double prime, etc., and then dividing 80 by 5, and that's where I get 16. And I divided this by 5 and this by 5 to say from 0 to 3. So now I've got it a little more straightened out. Now I'm going to look at the conditions. My conditions are that C1 or CI, C1 would be that x1, I forgot my I down there, x1 is greater than or equal to 4. And then C2 is that x2 is greater than or equal to 4. You get the idea. So there's 12 conditions for just a single. 12 conditions because there's 12 questions. To find the universe, I'm saying I have 12 boxes, I have 16 items. So combinations with repetition, 12 choose 16 gives me 12 plus 16 minus 1, or 27. Choose 16. That's my universe. S sub 1 would be that I'm applying that 4. So now I'm going to subtract 4 and subtract 4, and now I have combinations with repetition, 12 choose 12, and that gives me 23 choose 12. How many times is that happening? Well, the 12 conditions, and I'm just choosing one at a time. So this is all S1. Continuing on to S2. S2 would be the 2 conditions are met. So again, now I'm going to subtract another 4, which means 12 choose 8 combinations with repetition, which turns into 19 choose 8. It's 12 conditions, I'm choosing 2. And then I'm saying 12 choose 3 for, if I'm subtracting another 4, that leaves me with just 4. So here's the number of S3s. S4s, I've got 12 choose 0, because again I'm subtracting another 4. Well, 16 minus that many 4s is 0, and so that's S choose 4, and at this point it's very clear that I don't need to continue. And now I'm just shoving it all together into my formula. And again, it is not necessary for you to work that out to find a final solution, because quite often I'm really just looking for, are you able to correctly apply the principle and set it up correctly, just like this.